In this video, we're going to see how can we find the area of a polar region. So this is the thing that relates to finding the area under a curve. However, with a polar region, we often have a circular shape. So it's not quite the same as an under a curve, but rather the area in some relation to a circle. So suppose we have some region bounded by a polar curve between 0 or between A and B. So theta equals A and theta equals B. And A and B are within 2 pi of each other. And we want to find the area of this slice of region. Since this has a circular nature to it, what we're going to need to use is the area of a sector of a circle. So if we have a circle, the area of some slice of that circle is 1/2 r squared theta. So we have 1/2 r squared theta to find the area of this region. We want to find a way we can use that formula. Going back to how we found the area under a curve before, what we did was we sliced our region up into smaller pieces. And we can do the same thing, except we're slicing up the angle instead of slicing up the x-axis. So given some angle here being delta theta, some small little angle, we're going to zoom in on this region. So zooming in, we have that little delta theta. We have the curve doing something. Picking some random spot between that angle. Here, this point would be f of theta I plus 1. And this would be f of theta I. And somewhere in the middle, we've got f of theta I star. Just something between this random interval where we have broken this up into 1, 2, yada yada, until I plus 1, all the way up until b. We've split up this interval. Well, if I took this random f theta I star that is somewhere in my interval between theta I and theta I plus 1, and I said, I want to find the area of the circle here. That area of the circle will be a very good approximation for the area between theta I and theta I plus 1. So the area of this little sector is approximated by 1/2 f of theta I star squared, use it times delta theta, using this area of the sector formula. Taking the same idea, that is just one little area of the sector. So we're going to add up all of them and make that angle of theta really tiny. So area equals the limit as n goes to infinity of the sum I equals 1 to infinity of 1/2 f of theta I star squared delta theta. this is really the integral from a to b of 1/2 f of theta squared d theta. We have the limit of a sum. That is the integral formula. So finding the area of some region bounded by a polar curve is this integral formula. So taking a look at our first example of this, we want to find the area of one petal of the rose curve, r equals 5 cosine 3 theta. Before we can find and apply this formula, we want to figure out what is one petal of this rose curve, or what does this curve look like to begin with. So graphing this curve, we're going to plug in some values. I have picked out values that work nice, knowing that my angle is 3 theta. So every pi over 6 is going to switch the angle between a 0 or pi or 2 pi and a pi over 2. Like starting this off, when my angle is 0, I'm looking at 5 cosine of 0. 5 cosine of 0 is 5. So at an angle of 0, we have a 0.5. At pi over 6, this would be 5 cosine of pi over 2. Cosine of pi over 2 is 0. 5 times 0 is 0. When r equals when r equals, not r, when theta equals pi over 3, this would be 5 cosine of pi. Is 3 times pi over 3 is just pi. 5 cosine of pi is negative 5. 5 cosine 3 pi over 2 is 0 again. And 2 pi over 3 will make this 5 cosine of 2 pi, and we're back to 5. We can actually just repeat this pattern because now we've basically gone from 0 to 2 pi, dividing by 6. So we can repeat the pattern of this 5, 0, negative 5, 0, 5, and fill out this table as such. But I would encourage you to check those values for each of these yourself. Meaning we're going from 5 to 0. At pi over 3, we have a radius of negative 5. So we're going to go backwards away from that pi over 3 angle. Plot our point there. So far, we have this. Then we're back to 0. At 2 pi over 3, we have a radius of 5. We're about out to that point. And then back to 0 for an angle of 5 pi over 6. Then at pi, we have an angle of negative 5, which is the same as having an angle of 0. And we come back around. These 3 petals are supposed to be the same size. And they are unfortunately not the same size due to drawing, but if we had a graphing tool graph this for us, these 3 petals would be the same size. And then as this repeats, after here, the rest of this table would just go through those same pieces. Rest of this table, as we got down to pi. So 7 pi over 6 is back at 0. 4 pi over 3 is at 5. That point was already plotted. Back to 0. 5 pi over 3 is negative 5. That's back to this point up here. That was already plotted, and then back to 0. So this rose curve has 3 petals to it. We want to find one iteration of these petals, which would be any spot from 0 to 0. That it would go out, hit the farthest away point of the petal, and then come back. That's what our curve connecting our dots looks like, is this. So going from one of those 0 to 0s, to get one petal, we'd have the integral. Gonna pick the pi over 6 to pi over 2. Now we can use this formula. Our function is 5 cosine 3 theta. So we have 1/2 5 cosine 3 theta squared d theta. 5 squared is 25. And that's a constant, so it will come out. Cosine squared of 3 theta. And using the power reducing formula on cosine squared, that is 1/2, so 25 over 4. 25 over 2 times 1/2 is 25 over 4. The integral of pi over 6 to pi over 2. And the rest of the power reducing, we have 1/2 times 1 plus cosine of the angle doubled. So it's 3 theta, we're going to double that to become 6 theta. Now we can integrate this. That will become 25/4 theta plus 1/6 sine 6 theta from pi over 6 to pi over 2. And plugging in that upper and lower bound, we have 25 over 4 pi over 2 plus 1/6 sine 6 times pi over 2 is 3 pi. Minus, now plugging in the lower bound, pi over 6 plus 1/6 sine 6 times pi over 6 is just pi. Sine of pi is 0, and sine of 3 pi is 0, making this 25/4 of pi over 2 minus pi over 6. Pi over 2 minus pi over 6 is pi over 3. We get 25 times 4, or 25 over 4 times pi over 3, or 25 pi over 12. And there is the area of one petal of the rose curve using the formula for finding the area of a polar region.